So in this video we're going to be revising the topic shapes of molecules. So our aims for this video are to know what a lone pair is, and basically to know what all the shapes of different molecules are based on how many bonding pairs and lone pairs there are in the molecule. So first, what is a lone pair? Now to explain this I'm going to use a dot and cross diagram of water. So we'll have oxygen in the middle with two hydrogens attached to it. Yeah, those are two bonds, and then the rest of the electrons are not bonding. And basically, the lone pairs are these electrons here that aren't bonding with anything. So they're by themselves. So I'll just finish off this diagram. So they're by themselves, they're not bonding with anything, they are alone, and they're paired, if you like, a lone pair. So the reason why different shapes arise is due to the number of bonding pairs of electrons, number of lone pairs of electrons there are in a molecule. So it's based on the idea that a bonding pair, I'm just going to use the abbreviation BP, a bonding pair next to a bonding pair will repel less than a bonding pair next to a lone pair, which will repel less than a lone pair and a lone pair. So this idea of repulsion is what the shapes of molecules are based on. So if you take methane, for example, which is CH4, you will see that there are 4 bonds in methane. Now later on I'll show you how to work out how many bonding pairs and lone pairs there are in a compound, but for now I'm just going to tell you there are only 4 bonding pairs and no lone pairs. So methane has 4 bonding pairs which all try and get as far away from each other as possible. All these bonding pairs of electrons repel each other and they try and get as far away from each other as possible, and that results in a tetrahedral structure where the hydrogen atoms point in the 4 corners of a tetrahedron, and this is due to equal repulsion between each bond. So to describe why CH4 is a tetrahedron, you'd say that bonds repel equally, and so try to get as far away from each other as possible. Which results in a tetrahedron. This is the important bit, the fact that each bond repels each other equally. Now if you had lone pairs in amongst there as well, that would affect this shape, because the lone pairs would repel more, and so that means the bonds would be squashed together a bit more, and we'll see that happen in some examples later on. So before we can work out what the shape of a molecule is, first we have to know how many bonding pairs of electrons there are and how many electron pairs of electrons there are. And luckily there's a very simple method you can go through in order to work this out. So first I'm going to show you the different steps, and then I'm going to show you an example, work through an example. So the first step is you've got to work out find the group number of the middle atom of the molecule. I'll show you what I mean by that when I go through an example. You then add this to the number of bonds, and then the third step takes into account whether there's a positive or negative charge on the molecule. So if there's a positive charge, you take away one, and if there's a negative charge, you add 1 to the total, the running total, and then you divide your answer by 2. Now once you've done that, that will tell you how many electron pairs there are. To work out how many bonding pairs there are, that's just the number of bonds there are in the molecule. And to work out how many lone pairs there are, that's how many electron pairs there are left. So if we take an example, we'll use NH3, so ammonia. The first thing you do is work out what group the middle atom is. Now, the middle atom is going to be the one there's the least of, so that's N here. And so N is in group 5. The next step is to add to the number of bonds. Now here you can see there are 3 bonds, there are 3 H's attached to one N, so there are 3 bonds, so we're going to add 3 to this number. If there was a positive charge, we'd take 1 away. If there was a negative charge, we'd add 1, but there's not. This is a neutral molecule, so we're not going to do that. So then we add them all up, and then divide our answer by 2, and that gives us 4. That means there are 4 electron pairs. So how many bonding pairs are there? Well, there's 3 bonds. So there are 3 bonding pairs, and there are 4 electron pairs altogether, which means there must be 1 lone pair, so that it adds up to 4. So once you've worked out how many bonding pairs, lone pairs, and overall electron pairs there are in your molecule, you can then relate that to a shape. And what we're going to do now is go through each of the different shapes that you may come across. So if you had 2 electron pairs, both of which were bonding pairs, so you had 2 bonding pairs and no lone pairs, then that would give you a linear molecule, and that's the name you'd give it. If you wanted to draw it, then it would be drawn like this. And I'm going to use carbon dioxide as my example, because that is a linear molecule. And your bond angles you have to remember, your bond angle will be 180 degrees, as you can see from that shape. The next 2 shapes are based on the idea that you may have 3 electron pairs. Now the first shape, you would have 3 bonding pairs and no lone pairs. And that shape would be a trigonal planar shape. The reason it's called that is because I'm going to use BF3 as an example. You would have basically the F's pointing in the 3 corners of a triangle, and it would be flat, so planar means flat. The bond angles here would be 120 degrees. The other configuration numbers you may have is, again, 3 electron pairs, but this time only 2 bonding pairs and 1 lone pair. And if you had this configuration of numbers, you would say that this molecule had a bent shape. An example of this would be BF2-. So you'd have F and F down there, and you'd have a lone pair as well, and it would all be negatively charged. Now the bond angle here now is going to be slightly smaller than 120, because as we discussed before, a lone pair repels a bonding pair more than a bonding pair repels a bonding pair, and so we can say that this has a slightly smaller bond angle, about 117 degrees. Our next 3 shapes are based on the idea you may have 4 electron pairs, so each of these have 4 electron pairs. The first one has 4 bonding pairs and no lone pairs, and this one is called tetrahedral, and the reason for that is that the 4 bonds point in the 4 corners of a tetrahedron. An example of this would be CH4, and so to draw that, you put 2 of the H's in the plane of the paper, and then 1 goes into the paper, shown by a dashed line, and 1 comes out of the paper, shown by a wedged line. Now the bond angle here you have to remember, and that is 109.5 degrees. You must remember that number. The second shape you may come across is still 4 electron pairs, but this time you may have 3 bonding pairs and 1 lone pair. And an example of this would be NH3, and that shape has the name Trigonal Pyramid, because again it has 3 bonds, but this time it's not flat, it's 3D, it's in a pyramid shape. And to draw that, you would have your lone pair in the plane of the paper, one of your hydrogens in the other plane of the paper, and then one hydrogen going back and one hydrogen coming forward. The bond angle here will be slightly smaller than 109.5 because you have a lone pair here squeezing those bonds in. For each lone pair you add, you take away 2.5 from your original angle, and so the bond angle here for ammonia would be 107 degrees instead. The last example you might get is where you may have 2 bonding pairs and 2 electron pairs. An example of that is water, and we give the name bent. To draw that, you'd have oxygen, and you put the 2 lone pairs in the plane of the paper, and you would also put a hydrogen going into the page and a hydrogen coming out of the page. Now the lone pairs here squeeze the bonds in even more, because there's 2 lone pairs compared to 1 in NH3 and none in methane. So here the bond angle is even smaller, and you take off another 2.5 from the 107, so you end up with 104.5 degrees. Now when you draw lone pairs in these diagrams, it's really important you include the dots. Don't just draw the bulbs, if you like. You must draw these dots in these bulbs. The next number of electron pairs that you may come across is 5. So you might get 5 electron pairs, and then you have 5 bonding pairs, and you would have no lone pairs. And the name for this sort of shape is trigonal bipyramidal. An example of this shape is PCl5. And the way you draw it is put your P in the middle, and then you would draw 3 bonds in the plane of the page, these 3, and then 1 bond going in and one bond going out of the page. Sorry, I thought they're chlorine, sorry about that. So what you have here is these 3 bonds in the middle, all pointing towards the corners of a triangle, and then 1 bond coming up from that triangle, 1 bond coming down from that triangle. Now if you were to join these points together at the top and join these points at the end of the bottom, you'd have 2 pyramids, 2 trigonal pyramids. So that's what the name is based on, trigonal bipyramidal, i.e. 2 pyramids. There are also 2 bond angles you have to remember for this. There's one here, which is 120 degrees, because you've got these 3 bonds pointing towards the corners of a triangle, and then you have this angle here, which is 90 degrees. Finally, you may get examples where you have 6 electron pairs, and there are 2 examples of this. You may get 6 bonding pairs and no lone pairs, or you may get 4 bonding pairs and 2 lone pairs. So if we just start with the 6 bonding pairs, that would be called an octahedron, or an octahedral shape. And for example, you could have SF6. So that would be drawn like so. So you've got 1 bond going up and 1 bond coming down the plane of the page. Then you have 4 bonds in the middle, all pointing to the corner of a square, and all of the bond angles between these are all 90 degrees. Now if you have 4 bonding pairs and 2 lone pairs, then basically this is based on octahedron, but you lose the top and the bottom bond. So what you get is, so this one could be xenon tetrafluoride. You'd have the xenon in the middle, and then you'd have 2 lone pairs, one going up and one going down, and then you'd have your other bonds still in place around the xenon. Now, because the 2 lone pairs are opposite each other, they cancel each other out. If you like, this lone pair will push these bonds down, but this lone pair would push them back up again an equal amount. So the bond angles here are, again, 90 degrees, as those lone pairs have no effect. That's all the shapes that you need to know. If you would like any more help on these, then please come and see me.